Okay, yes, I'm Estelle Lubbe. Thanks for the introduction. Today I'll be talking about state estimation for a commercially available hexapod robot. I'll start off with the introduction. I'll discuss my goal, background, and methodology. I'll discuss the kinematic model, the sensory system, the state estimation for the robot, as well as the implementation of all of the above, and I'll conclude with my results. I want to start off with a very important question wherever it comes to real-world implementation of our research, which is why legged robots. For us, the ultimate goal in the development of legged robots is to take full advantage of their ability to navigate in unstructured environments. This will allow their applications in, for example, search and rescue missions. We look specifically at hexapod robots because they can easily maintain static stability on a minimum of 3 legs, in which they are more efficient in walking as well. They exhibit robustness even with leg defects, and they can support more weight than bipeds and quadrupeds. Their robustness and abilities make them a better choice for a wider variety of applications than other legged robots. The main limitation when it comes to the development of legged robots is the complicated control algorithms needed for walking in uneven terrain. The influence of this complexity is made clear by the fact that most literature only focus on walking on flat or slightly uneven terrain. These control algorithms need information that is provided to them by the robot state estimator, which uses sensory measurements provided by the robot sensory system. In order to take full advantage of what a hexapod robot has to offer, we need to focus on the development of control algorithms that will optimize their performance and efficiency. This leads to our next main limitation, which is that most robotic research in the industry and academia makes use of custom-designed hardware and software. This means that a lot of time and resources are being spent on the development of a robot platform with a good sensory system and reliable real-time state estimation, which takes economic and human resources away from control algorithm development and testing. The purpose of this study was to address some of these limitations by identifying a state estimation methodology that can be implemented on a commercially available hexapod robot using only low-cost commercially available sensors. This will provide a quicker, more cost-effective solution that will produce a platform that researchers and developers can use for control algorithm and development. So from literature, it was found that for the control of a legged robot, the state estimation has to provide a full 6 degrees of freedom pose information. This translates to translation and rotation in 3 perpendicular axes. We also need to take into account that the robot will ultimately walk on uneven terrain, which means that the specific gait can't be restricted. Furthermore, we need to take into account that legged robot locomotion inherently involves intermittent ground with the contact, which means that the controller needs fast and precise knowledge about the state of the robot at all times to maintain stability. Also, the sensors should be kept to a minimum. This is because legged robots usually have a limited payload, available energy, as well as onboard computing power. Lastly, control and localization should only depend on proprioceptive sensors. The information quality and reliability of the exteroceptive sensors are not fit for stability control in uneven terrain navigation. For the study, a full post state estimation presented by Blush et al. For a quadruped robot was chosen. This state estimation makes no assumptions about the environment or the location where the robot is located at or the gait it uses to navigate around. It estimates the foot positions as well as the pose of the body in a fixed inertial coordinate frame. The estimation is done with the observability constraint extended Kalman filter, which fuses the kinematic model of the robot with onboard IMU measurements. This estimation is also of a very generic form, which means that it can be implemented on other robots and other sensors can be added into the estimation as well. So taking into consideration the requirements as well as the state estimation methodology, the Phantom X Mark II hexapod robot distributed by Trossen Robotics was chosen as the base platform for the study. For that platform, the kinematic model was derived using the Denner-Witt-Haltenberg method. The kinematic model specifically computes the forward kinematics of the robot, meaning that given a set of joint angles, it calculates the foot positions relative to the body coordinate frame. Firstly, the kinematic model for a leg was derived, which were then translated and transformed into the body coordinate frame to compute the entire kinematic model of the robot. Again, taking into consider all the requirements, a sensory system was designed. It consists of an IMU that was mounted onto the robot, joint position sensors that were included already in the robot's servo motors, which were used as input to the kinematic model, as well as 4 sensors that were integrated into the robot feet to record accurate ground contact of the feet. All of these sensors were integrated onto the robot, and a single board computer was used to handle the sensor data acquisition. Without going into too much details about the state estimation, the state definition of the extended Kalman filter was derived, as you can see at point number 1, where R is the position and V the velocity of the robot expressed in the inertial coordinate frame. The rotation from the body coordinate frame to the inertial coordinate frame is represented by the criterion Q. And then the kinematic model was considered by including foot positions P1 to P6. And then lastly, with regards to the IMU, BF is the accelerometer bias, and B omega is the gyroscopic bias. Thereafter, the corresponding state error vector was derived, the filter prediction model, the filter measurement model, and then we performed the state estimation for a the non-linear system defined. The extended Kalman filter equations were then used for the prediction and the update state, which concluded the state estimation of the robot. The state estimation and the kinematic model were executed in MATLAB. To initialize the noise parameters, the sensor data sheets were used, whereafter it was empirically tuned to get the best results. For the initialization of the extended Kalman filter, motionless sensor data was recorded for all the variables in the state definition, except for the foot positions, which were calculated by the kinematic model translated into the inertial coordinate frame. Because the control is out of the scope of the study, we used an open source control to validate the state estimation. The validation was done with ground truth measurements of a Vicon motion capturing system here at the CSIR, which tracks rigid bodies in 3D space. So some of the experiments. In this first experiment, we recorded the position of the robot for 2 different gates. You can see very accurate estimation. Keep in mind that this is done without any exteroceptive sensors. The difference between the ripple and the tripod gate is due to the robot vibrating more, so there's more errors in the sensors. In the second experiment, the z-axis position and velocity was tested. You can see almost no drift in the z-axis position and a really small drift in very small RMS error in the velocity estimation of 0.0183 meters per second, which means that the velocity can be tracked very accurately. In this first test, we tested the yaw, pitch, and roll. Here the robot performed a set of clockwise and anti-clockwise turn, followed by a set of forward and backwards tilting, and ended with sideways tilting. Again, very accurate estimation was seen, with RMS errors not exceeding 0.01 radians. Lastly, the velocity of the robot was tested. Here the robot walked just over 4 meters, and again very accurate estimation was observed. This is due to the velocity being fully observable, with the RMS errors not exceeding 0.04 meters per second. So the methodology presented targets the development of a feasible solution to provide a low-cost hexapod platform with reliable state estimation for the purpose of control algorithm development. The experimental results showed excellent comparison with the Vicon ground truth and consequently validated the framework presented by Bluch et al. On a quadruped for this hexapod. Furthermore, in terms of future work, we're looking at now developing control algorithms for the robot and also including other sensors to better the global position estimation.